You know, for over half a century, one single material has basically powered our entire world: silicon. Its progress has defined, well, everything. But that golden age, it's hitting a wall. We are running headfirst into the fundamental limits of physics, and that's kicking off an incredible race to build a machine that will define the next generation of AI.
Okay, let's really get into this. The silicon chip, the thing that runs our phones, our cars, our lives, it's starting to sputter. And the problem isn't just about making things smaller anymore. No, it's about a fundamental traffic jam in how our computers actually think, and an energy bill that's getting just completely out of control.
So, this big problem, it actually has a name: the von Neumann bottleneck. Now, it's a design flaw we've kind of known about and lived with for decades. But with the insane demands of modern AI, which has to chew through mountains and mountains of data, this little flaw has mushroomed into a full-blown crisis.
And when you get right down to it, the problem is surprisingly simple. Your computer has its brain, the processor, in one place, and its memory in another. And it has to constantly shuttle data back and forth between them. This creates a massive traffic jam. But it's not just slow. It's an energy hog. We're talking about wasting way more power just moving the data around than actually doing the calculation.
But you know, out of every crisis comes opportunity. And in this case, we have two heavyweight contenders stepping into the ring. And they're not just offering an upgrade, they represent totally different ways of thinking about computing. One looks inward, to the most efficient computer known to man, and the other looks outward, to the very fabric of reality itself.
All right, first up, the brain's apprentice. We're talking about neuromorphic computing. And the core idea here is as simple as it is profound. What if we built a computer that works less like a calculator and more like a biological brain?
So instead of one big central processor bossing everyone around, these chips are more like a massive interconnected web, a social network of artificial neurons and synapses. And here's the key: the memory and the processing are woven together, completely shattering that von Neumann bottleneck we were just talking about. So, how in the world does it work? Well, these systems use something called spiking neural networks. Now, think about your laptop. Its internal clock is always ticking, always running, always burning energy. But these neuromorphic neurons, they're mostly just chilling out. They only activate and spike when they receive important data. It's an event-driven approach, which means they only compute when they absolutely have to. And the efficiency you get from this is, well, it's just staggering. To put it in perspective, think about your own brain. It's performing these unbelievably complex tasks, from understanding what I'm saying right now to processing everything you see, all while running on just 20 watts of power. That's less than a dim light bulb. And that is the benchmark neuromorphic computing is chasing. So, what's the upshot of all this? It means this architecture is tailor-made for AI that has to live out in the real world. We're talking about autonomous drones, smart medical sensors, robots with human-like reflexes, all of them learning and adapting in real time without having to call home to a massive data center. Okay, so that was contender number one. Now let's switch gears completely. If neuromorphic computing is inspired by inner space, by biology, then quantum computing is inspired by the absolutely wild, mind-bending rules of the subatomic universe. Right, so your computer runs on bits, simple on or off switches, a 0 or a 1. That's it. Quantum computers, though, use qubits. And as this block sphere shows, a qubit isn't just a simple switch. It's an entire world of possibilities. How is that even possible? Well, it comes down to a quantum principle called superposition. Basically, until you actually measure it, a qubit can exist in a combination of both 0 and 1 at the exact same time. And that ability to hold multiple values at once, that's the secret sauce that unlocks its incredible power. But it gets even crazier. When you link these qubits together through another strange property called entanglement, where their fates become intertwined, the computational power just explodes exponentially. A system with n qubits can explore 2 to the power of n possibilities all at once. That allows it to tackle problems that are simply, fundamentally unsolvable for even the biggest supercomputers on Earth. But let's be super clear here. You're not going to be checking your email on one of these things. Quantum computers are specialized giants. They're designed for monumental tasks, like simulating new molecules to discover life-saving drugs, designing revolutionary new materials from the atom up, or, breaking most modern encryption. Okay, so we've got the super efficient digital brain in one corner and the reality-bending supercalculator in the other. How do they actually stack up? Well, here's the twist. They're not really competitors.
They're specialists, designed for entirely different arenas.
And this table really lays out the stark contrast. Neuromorphic computing is all about low-power, real-time efficiency for things like pattern recognition. It sips power in the milliwatts. Quantum computing, on the other hand, is a power-hungry beast that needs to be cryogenically cooled, but in return, it delivers this unparalleled computational force for massive simulation and optimization problems.
This all leads to the big question, right? Is the computer sitting on your desk about to become a museum piece?
And the answer, you'll be happy to hear, is a resounding no. Classical computing is fantastic for all the general-purpose, everyday things we need to do. These new machines aren't replacements, they are powerful specialists. Neuromorphic chips will be like hyper-efficient coprocessors, while quantum computers will be these massive giants you access through the cloud, like a strategic superweapon.
So the future isn't about one winner taking all. It's about creating what's called a heterogeneous computing environment. Really, it's just a fancy way of saying we're building a team of specialists, where each type of computer plays to its unique strengths.
And this scenario just perfectly shows how it all comes together. So, step 1, a quantum computer solves the massive optimization problem of designing the absolute perfect jet engine. Then, step 2, a classical supercomputer runs all the detailed, heavy-duty flight simulations. And finally, step 3, a tiny little neuromorphic chip sits inside that engine for its entire lifetime, monitoring its performance in real time and using less power than a light bulb.
So when is this future gonna get here? Well, neuromorphic chips are already being rolled out, and you can expect them to be common in robotics and sensors within the next few years. As for true fault-tolerant quantum computers, the ones that can solve those massive commercial problems, they're probably still about a decade away. But, and this is the cool part, you can already access early versions through the cloud today. Which brings us right back to our central question. In this tale of two brains, one biological, one subatomic, which one truly wins the right to power the next age of computing? The answer is, that's the wrong question. The real insight is this. The end of silicon's dominance is forcing this Cambrian explosion of specialized computers. It's not being replaced by one new monopoly, but by a whole ecosystem of different brains. The future of intelligence isn't about finding one master computer. It's about building a team of specialists and knowing exactly which brain to use for the job at hand.